Hello students, welcome back to chemistry class. Let me ask you something. Why do we add sugar to tea when it's hot and not when it's cold? You've noticed, haven't you, that sugar dissolves faster and in greater quantity in hot tea than in cold water? That everyday observation introduces us to the fascinating idea of solubility and how it changes with temperature. Solubility is defined as the maximum amount of solute that can dissolve in a given quantity of solvent at a particular temperature to form a saturated solution. Temperature plays a vital role here. For many substances, solubility increases with temperature. But surprisingly, for some, it decreases. We often represent this relationship through solubility curves, where the x-axis shows temperature and the y-axis shows solubility, that is, grams of solute dissolved in 100 grams of water. Unlike gases, where solubility strongly depends on pressure, the solubility of solids in liquids is mostly unaffected by pressure. So, next time you add sugar to your tea, remember, you're practically plotting a solubility curve in your cup. Now, let us dive deeper into solubility curves. A solubility curve is simply a graph showing how solubility varies with temperature. On the horizontal axis, or x-axis, we place temperature of the solvent. On the vertical axis, or y-axis, we plot solubility, usually expressed as grams of solute per 100 grams of water. Each substance has its own unique solubility curve. For example, potassium nitrate shows a steep rise in solubility with increase in temperature, whereas sodium chloride shows only a slight increase. Such curves help us predict whether a solution at a given condition is unsaturated, saturated, or even supersaturated. So, these curves are not just diagrams, they are chemical maps guiding us through the world of solutions. For many ionic salts, solubility rises sharply with increasing temperature. A classic example is potassium nitrate, which shows maximum solubility near 100 degrees Celsius. Other examples include potassium chlorate, sodium nitrate, copper sulfate, and ammonium chloride. Why does this happen? Heating provides water molecules with more kinetic energy. This allows them to overcome the strong ionic bonds holding the solute particles together, so more solute dissolves. Industries actually use this property. In crystallization of salts, substances are dissolved in hot water where solubility is high. Then, on cooling, the solute separates out as pure crystals. Isn't it amazing how your hot cup of tea and an industrial crystallizer are governed by the same principle? Some substances show only a slight increase in solubility with temperature. Sodium chloride is the perfect example. Whether it is room temperature or 100 degrees Celsius, its solubility changes very little. Other salts like potassium chloride and calcium hydroxide below 70 degrees Celsius also show this minor variation. The reason is that molecular interactions in these salts are already quite favorable, so additional heating does not make a big difference. That is why in saline water, like seawater, increasing the temperature does not really dissolve much more salt. The ocean remains salty regardless of summer or winter. Interestingly, there are a few salts whose solubility actually decreases with temperature. For example, calcium sulfate becomes less soluble as the temperature rises beyond 70 degrees Celsius. Similarly, calcium hydroxide also shows reduced solubility at higher temperatures. Why does this happen? Heating disturbs the hydration shell around these ions, making them less likely to remain dissolved. In industry, this phenomenon creates real challenges. When water containing calcium salts is heated in boilers, salts like calcium sulfate come out of solution and deposit as hard scales on the inner walls. This is the reason why boiler scaling occurs, reducing efficiency and increasing maintenance costs. Now comes a very special case, sodium sulfate decahydrate. Its solubility curve has an unusual sharp break at 36 degrees Celsius. Below 36 degrees, the compound exists as a hydrated salt, sodium sulfate decahydrate. Above 36 degrees, it loses water of crystallization and becomes anhydrous sodium sulfate, which shows lower solubility. This sudden change in the curve makes sodium sulfate an excellent example of how temperature can influence the stability of hydrates. Solubility curves are not just theory, they have countless applications. In medicine, pharmacists use solubility data to know exactly how much drug can be dissolved in a solvent to prepare syrups and injections. In research, chemists choose the most suitable solvent at a specific temperature for extraction of chemicals. In purification, crystallization is used. As a solution cools, the salt with lower solubility crystallize first, leaving impurities behind. Solubility curves also allow us to calculate how much solute will crystallize out if a hot saturated solution is cooled. So, whether it is in your medicine bottle or a chemical laboratory, solubility curves are a powerful tool. Alright, students, let's quickly recap what we have learned today. Solubility curves show us how solubility of different salts changes with temperature. Some, like potassium nitrate, increase sharply. Others, like sodium chloride, increase only slightly. A few, like calcium sulfate, actually decrease with temperature. Sodium sulfate decahydrate shows a sharp break at 36 degrees due to change in hydration. Applications of solubility curves extend from medicine preparation to industrial crystallization to solving real-life chemical problems. So now you know, when you stir sugar into hot tea, or when industries recover pure crystals, it all comes down to the magical relationship between solubility and temperature. I hope this session helped you see how chemistry connects your daily life to industrial applications. See you in the next concept of water.